let's pay attention here.
All right, so we are the Robotic Recharging for Lunar Scout Exploration Group. I'm Bruno.
I'm Alan.
I'm Nate.
And so our problem and motivation was there's been recent discoveries of lunar pits, skylights, and caves, and we want to robotically explore these for potential human habitation later on in the future. And for rover exploration, one battery cycle is insufficient for almost every type of extensive exploration we're looking to do. And another problem in these areas is that there's little sunlight in the pits and in the caves. So traditional solar panel charging on rovers is out of the question. And so that makes recharging essential, and furthermore fast recharging, because it makes no sense to spend most of your time sitting around docking and charging than exploring. And so here are some numbers. So a typical planetary rover might explore 5,000 square meters of relatively easy flat terrain. So with 300 watt-hour capacity and 100 watts of operation, that's 0.5 meters squared per second of exploration rate. And so you get the size of an American football field, and there's a photo there comparing the pit crater compared to a football field at Sandia. And so recharging equates to more exploration. And so our project goals were to investigate effective charging methods, design the prototype robotic recharging system, and demonstrate the proof of concept. And our method in the idealized system will be to have solar energy collected above the surface and then transmitted via a vertically dangling tether with conduction and induction docks at the bottom, which will then connect to the rover and allow it to recharge. And this will allow for faster, more consistent recharging. It will reduce our dust tolerance concerns of lunar regolith accumulation, and it adds redundancy and accounts for misalignment in docking.
So our approach is a little bit different than anything that's been done so far. Earth robots do use autonomous docking systems, but they generally operate in highly structured and clean environments. The moon is very unstructured, it's very unpredictable, the terrain, and it's covered in dirt. Honeybee did develop a dust-tolerant connector for use on the moon, but it requires significant horizontal reaction forces to make the connection. It's intended to be manipulated by an astronaut. It can be adapted for a rover, but it still requires a lot of horizontal force. And if we're charging from a dangling tether, you don't have that horizontal force. NASA's Chariot rover uses pure induction. The reason we went away from using only induction is because we wanted the redundant system of conduction and induction, and because conduction is more power efficient than induction is. A little bit of background. Conduction requires two physical contacts between the wires. It's the most simple, it's the most understood, it's very efficient. The disadvantages on the moon are that it's susceptible to dust clogging. If you don't get a physical contact between the connectors, you don't get power transfer. That requires high precision to make that connection. Induction, on the other hand, can be done remotely without contact. The advantage is that it's less susceptible than to dust clogging because it can transfer through some amount of dust. And it also allows for some more misalignment. You don't need as much precision. The disadvantage is that it is a lower efficiency. Commercial products are somewhere around 35% efficient, while state-of-the-art systems might be somewhere around 85%. This results in a slower power transfer, which means less exploration.
So, as mentioned, one of the big challenges of performing robotic exploration missions on the moon is the lunar regolith. Lunar regolith is composed of a heterogeneous collection of fine particulates that are abrasive and have electromagnetic properties that we are very aware of due to the nature of our charging solution. So, to evaluate how much of an effect the regolith might be on a potential charging solution, lunar simulants exist which mimic various electromagnetic and mechanical properties of the regolith on the moon. Our quote-unquote dirty trials, where we tested this mechanism with regolith applied to it, we used lunar simulant JSE-1A, which has similar mechanical properties and has been used in previous studies. While it doesn't have the same iron content of the regolith found on the moon, during testing we found that the static forces created by the induction pad was enough to have significant accumulation on the induction pads. So, to further characterize the interaction of various interfering materials with the induction charging pad, we looked at how the different materials affected the efficiency of the power transfer from the power source with the magnetic coils and how much power is received by the receiving end. So this being a consumer electronic device had an ideal efficiency around 30%, and with 2.5 millimeters of the lunar stimulant in between the plates, we found the efficiency dropped several percent. While we don't expect this to be a major concern in our testing due to the fact that the amount, 2.5 millimeters of separation with stimulant, we don't expect that that much stimulant would accumulate on our vertical testing configuration.
Okay, so our fundamental design concept was that we have two parts, and we have a passive capture mechanism located on the rover, and then we have our diamond invertible tether with electric current running through it, which will have the contacts to cause charging. And so in this video, you're just going to see the rover docking with the tether. So the rover will drive forward, straddle the tether will now pull up and lock into position, and then recharging will be in. And now you're going to see it again from the top angle. And what we liked about this design was that it predicted good reliability, and it was good against dust and misalignment tolerance, as well as the redundant charging system we could incorporate. Our other concepts that we thought about suffered from predicted low reliability, insufficient reaction forces, regolith accumulation, high mass, and very high complexity. And so here is the finalized design, our CAD model. And so what you can see here is this plate, right here, this horizontal plate, the blue, the green, and the triangular arms are all attached to the rover as the passive capture mechanism. And then along this vertical induction pad and this center cylinder with the orange top is the part connected to the tether that would be actuated up to connect to the rover.
We're going to pass these around. You can look at them if you want. Be careful with the plastic parts, they're brittle.
All right, and here you can see part of our passive alignment mechanism. This red is the cam profile. And so as the shaft is pulled into alignment, this pin would hit the cam profile and rotate it into a locking position here, and then it would continue to be pulled out so the pins could align. And so here you can see a video of just a dry run with our docking mechanism. So it's being actuated upwards by the tether, and it's going to slide into this cone right here, and then the passive alignment mechanism just went into effect, rotated it, and it gets pulled up into position until the contacts are reached. You'll see it again from the side, and these two LEDs will light up to show electrical contact. Right there. And now there's the undocking portion. There's the passive release mechanism, which is helped out by these springs that we have on both sides to push down. And so it undocks in that way.
So the original test plan that we devised included 120 different trials where the prototype would be mounted onto the cave crawler robot. Cave crawler would then be driven towards the hanging tether and attempt to make an electrical connection. We defined a successful trial as one that achieved a 5-watt power transfer by measuring the current voltage on board the rover. We plan to test across 5 different orientations. That includes flat, roll to the right, roll to the left, pitch up, and pitch down. It simulates driving on different slopes. Also approaching the tether from 4 different angles relative to the slot on the tether mechanism, coming from the front, back, left, and right. We would get 3 repetitions of each test, and we ran everything in a clean and then a dirty. That's 120 trials. The result would then be percent success for conduction, induction, and either or. The test plan that we actually executed had a few minor adjustments. A successful transfer was defined as one that just lit up the LED lights instead of trying to achieve a 5-watt power transfer. We combined roll right and roll left into just a single roll because the device is symmetric. Roll right and left are really the same thing. We also renamed the approach angle to headings northeast, south, and west with respect to the tether, just to keep things straight. During the clean testing, we added 4 additional trials of a slightly smaller pitch down angle. As you'll see why in the results. For dirty testing, we only tested the flat orientation because it struggled enough that any further testing didn't seem reasonable. This is a video of the flat configuration, 0 roll, 0 pitch. Cave crawler is approaching the tether, which is in the foreground on the right here. Once it straddles the wire, the tether is actuated upwards. It slides into axial alignment, and then it will turn into rotational alignment. When it reaches the top and the connection is made, 2 LED lights will turn on right here. Then it releases using the passive release springs. And finally, cave crawler will drive away. This is just a picture showing how we induced a 12-degree roll. This wooden platform lifted 2 of the rover's wheels, and it was long enough to still drive forward and test the device in the same manner as the flat. This is a short video showing one of those tests. The difference is that there's now an angular misalignment between the tether and the rover, and so you'll see that it will pull it first into axial alignment, and you'll notice that there's some shaking which is caused by additional friction due to the moment that is now on the system. This is what the pitch up configuration looked like. Instead of driving the rover forward, we actually actuated the tether into the robot because it can't drive forward in this configuration. And this is pitched down.
So for the dirty testing, we applied the lunar simulant to both ends, the rover end and tether end of the mechanism, by taking a small cup and applying a copious amount of simulant to both ends. This would represent the worst case scenario of lunar regolith accumulation, where there actually, after it was applied, there'd be like several mounds of simulant on any horizontal planar surface. This is just a picture showing how, similar to the pitch up and pitch down configurations, for the dirty testing, we kept cave crawler stationary and moved the tether and actuated it into the lock position. In the next, this short video, we'll demonstrate the dirty testing in the nominal configuration where cave crawler is flat. Similar to the roll angles, you'll see that, especially on the descent, significant jerking and shaking as the regolith, especially up on the cam profile here, slides against the alignment nut. It's worth noting that it does make electrical contact with each LED representing the induction power transfer being successful and the conduction power transfer also being successful. So these are the results of our experiment. The nominal configuration is, as I said, just a flat cave crawler is on a flat plane. Roll right, pitch up, pitch down. And the y-axis represents the success rate, where success represents a successful approach, engage, and power transfer of either the electrical system, which required either the conduction or induction achieving power transfer, then a successful disengage and drive away. So you'll notice that the pitch down of an angle of 11.5 degrees failed every time. This is definitely notable, and we tried a less aggressive angle of 6.5 degrees, where of the 4 trials, it did succeed every time.
Alright, so testing to failure, we had 3 types of conditions that we would consider our testing and failure. So there's docking failure, which would be straddling the tether and raising up. There was electrical connection failure, which means the electrical contacts would not signal or some other issue would arise with that. And then undocking failure, where it would, the tether and the rover would not disengage for some reason. And so the configurations, certain configurations found that were prone to failure. That first one, south heading, which means coming in from the backside of the tether with the induction pad facing the opposite direction of the rover. It proved proved to have some problems, like right here, you can see the top of our cam profile hitting the aluminum and preventing it from raising. The second one pitched down at 11.5 degrees. It's very difficult to tell, but the cam profile jumped the nut and basically wedged it between the two plastic parts, making it unable to align rotationally. And the final one here, excessive simulated accumulation on the top right here, it provided enough friction that it was unable to undock successfully. And so all of our failures were mechanical, docking, undocking, no electrical failures. Once induction didn't turn on, but we saw the conduction power going through. So with the south heading of the 11.5 pitch down configuration, that was 16 out of 24 failures, 67% of our failures. And then of our remaining 8 failures, they were all simulated jamming, which is 33%, which you can see in this chart here. And between undocking and docking, you can see that undocking was 25% of our failures, and docking was 75% of our failures.
The relevance of this testing to an actual lunar mission is that the passive alignment concept does work in principle, but it is sensitive to regolith contamination. The upside is that the levels of simulant that we tested with are much higher than what we'd actually expect to see in a mission. We poured literally piles of regolith on all of our surfaces, when in reality the tether should never touch the ground, and there should be very little simulant accumulating on it. Downside is that in a hard vacuum, real regolith increases in cohesion and adhesion forces due to the low pressure, which we didn't experience on our testing here on Earth. Another benefit of working in the moon is that the reduced gravity reduces the frictional forces. This is because gravity asserts a moment on the device when it's at any orientation other than straight up and down. To compensate for the reduced gravity, a greater spring force would be needed on the release mechanism, but this is achieved by increasing the spring constant. And of course, any flight system would have to be made entirely of space-rated materials, which our prototype was not. Potential improvements to the configuration as it is right now, what I call the dual configuration, would be smoother contact surfaces, which could be achieved through tighter machining tolerances and more polish on the surfaces. A greater spring constant should reduce undocking failures because it provides the force necessary to overcome friction. Some kind of a shield on the tether should help reduce regolith accumulation that might rain down from the surface of the skylight. And adding fiducial markers could allow the rover to assert which orientation it's approaching from and avoid the few problematic approach angles that we observed. An alternate strategy would be to reduce to just a single configuration where you use induction only. The advantage here is that you reduce risk and complexity because you don't need this tight mechanical precision and this mechanical device to align. You don't have any sliding surfaces, and most of our failure modes are then eliminated. The trade-off is that there's a slight loss of efficiency, but with the state-of-the-art system, 85% efficiency is still fairly reasonable. Any future testing also would have to be done in a hard vacuum in extreme temperatures to verify that the system would work on the moon.
So the conclusion of our project is that we design and create a prototype that demonstrates the feasibility of our approach. Improvements can be made given that all the failure cases were well defined and therefore hopefully avoidable, and that the failures due to simulant accumulation are far above what we would expect in an actual mission. Another important thing we learned is that the core concept of our design was that we incorporated both induction and conduction charging, while in fact that, with the exception of one trial, was never beneficial, and that avoiding the precision required by conduction contact means that we could go with a much simpler and more robust charging configuration.
I really appreciate the amount of different parameters you guys tested over. But I will notice that you stopped the robot at some point for each of the tests. How did you determine when to stop moving? And is there any intuition you can give about whether that variable changed with the different parameters?
The rover was driven manually, and so it was not exactly repeatable. But in an autonomous system, you can imagine including photo eyes on either side of the little Y-shaped piece that would sense when the tether passed through each checkpoint, and you would know then when to stop.
So is that the objective that the driver had when he drove the robot?
Yes, just to get it past those the first two bends in that piece.
Let's see, there's, the cam angle is how much
45 degrees.
and why?
A shallower angle increases the friction force and the tension force that you would need to actually swivel the device. A steeper angle would reduce that force, but it makes the entire device longer and larger. So there's a trade-off.
The guide rods that you had for the release springs didn't slip in the bushing, and now they do. What happened?
We ground them down.
Could you go back to the slide where we looked at the let's see, it was looking at the induction, so it's very close to the beginning of the presentation, and it looked at the drop of efficiency with gap. Did you try a conductive material in there? Or something with the iron content?
That's BP1 lunar simulant. We don't know the exact iron content of the material.
Okay. Others?
So you look at the spinning of your, so what if your end of your tether is spinning wildly, like you can't really approach it from one side or from the correct side?
We didn't observe any spinning. Part of that could have been because we were attaching power cables from the side, which maybe kept it in one orientation. But in the case where you do accidentally approach from the south side, and you do encounter that the peak of the cam profile, you could always back out and try again. And statistically, if you do that 2 or 3 times in a row, your odds of hitting that every single time are very small.
I'm just thinking if this thing is on a really long cable and all of your power is coming down that really long cable, I think there's going to be a lot of spinning.
It has to dissipate eventually. I mean, what would cause the spinning?
Well, you hitting it. If you come in and then detach from it, that's causing forces on it.
Right, but then the next charge cycle would be, 10 hours later or something.
Yeah, but if you're talking about, it's spinning, wait, come up to it, oh, we were the wrong way, come out, come in again.
Well, then you're playing the odds that you hit that exact precise point where it doesn't slide to the right or to the left every single time you attempt, which is unlikely.